Started. Welcome to day 14. First few administrative announcements. As a reminder, which I also reminded about last time, your draft of the Wikipedia article is due today. Let's call it by midnight today. So please get that in, and if you have questions that come up, please let me know between now and midnight, or let the TAs know. There was a question that came up already about formatting at this stage, and to be honest, however you want to format it is fine, knowing that eventually it will have to get into the Wikipedia article format. If you already have it formatted that way, then I would just recommend you do a preview in the sandbox and then export as PDF, and then you can submit it that way. If you have it formatted as a Word document, that's fine too. It just is a matter of if you want to front load or back load that aspect of the work. So are there any questions on the Wikipedia article draft? Okay, the other thing is that the midterms are now available for pickup. So if you want your midterm returned to you, just stay after class and you can walk over to my office and I can return it to you. And I'll make the key available through the website. Maybe the TAs can send that out over email as well. Perfect. Okay, let's jump in to today's class, which is one of my favorite topics, or it's actually multiple topics grouped into one lecture. But one of my favorite areas of research in organometallic chemistry and organometallic catalysis, which is metal-mediated addition to CC pi bonds, mechanistic aspects of those additions, and then translating those mechanistic insights into preparatively useful protocols. So the bulk of today will focus on the Wacker oxidation or Wacker type alkene additions. We'll also touch on, if there's time at the end, on Heck type alkene additions. It might go a little bit long, so that might be moved. Parts of that might be moved into the allylic substitution lecture, but those go nicely together anyway. But before jumping into that area, which that will mostly involve reactions catalyzed or promoted by palladium salts, we'll first introduce a concept or a series of selection rules for pi bond addition or additions to metal pi complexes more generally, specifically for 18 electron complexes. So what we'll deal with a lot in the palladium space are these square planar D8 16 electron complexes, and this series of rules is specific to 18 electron complexes. So we're going to introduce this, and then the rest of the lecture will focus on something that's slightly different from this. So I want to be crystal clear about that from the outset. So these are called the Green-Davies-Mingos rules, named after three Oxford chemists, Malcolm Green, Steve Davies, and Michael Mingos. And this series of rules describes, it's essentially a predictive framework to be able to predict, sorry, I'm just getting some notifications. Silence my notifications. To predict where generic nucleophiles will engage metal pi bond containing systems when there are multiple sites of potential attack. And why I specified that these selection rules are for 18 electron complexes is because that then is already dictating that the types of additions we'll be focusing on are those that are outer sphere. So think here like addition of a hydride, or addition of a deprotonated malonate or something like that. These are going to be outer sphere additions, so we don't have the complication of pre-association to the metal center. In the palladium work that we'll cover later in the lecture, you have this added complication of two mechanistic possibilities of syn or anti-type nucleophile. halidations. Okay, so let me just read through these rules, and then in the problem of the day number 1, we'll see how this manifests itself, and we'll work through other examples of this as we go throughout the class. So the first rule is that nucleophilic attack is preferred on even numbered polyenes. So here we're using polyenes in the most general sense of polyenes, that is even including aromatic compounds, just any compound that has multiple pi bonds in conjugation with one another. The second rule is that nucleophiles will preferentially add to acyclic polyenes rather than cyclic polyenes. And there's that, I think, is a manifestation both of sterics and a manifestation of the fact that a lot of the cyclic polyenes that you'll encounter have some aromaticity associated with them. Not all, but some. Nucleophiles add preferentially to even hapticity acyclic polyene ligands at the terminus and odd hapticity acyclic polyene ligands at this might be it. Is it correct or a typo? At a terminus. Okay, that is right. And if oh, sorry. Okay, there's a. I confused myself because this second clause. So the nucleophiles will preferentially add to terminal positions if the metal is highly electrophilic. Otherwise, it can add to an internal cycle. So what do I mean by a metal being highly electrophilic? Here I'm talking about generally late transition metals. So your palladium, your platinum, your iridium, your rhodium, etc. in a high oxidation state. So if it's palladium +2, +3, +4. Otherwise, with earlier transition metals in lower oxidation state, think about internal addition. So if you have a low valent tungsten al complex, then this is capable of adding a nucleophile at the internal position of the al to give what would be a metallocyclobutane product, for example. Okay, let's work through a few. And so here's a visual, down here is a visual depiction of these selection rules, which to me is easier to understand and remember than thinking about these rules written out in text. Okay, let's work through a few examples now. So problem of the day number 1 shows 3 representative examples here. You can do the electron counting yourself if you're not convinced, but these are all 18 electron complexes that fit in this framework of Green, Davies, Mingos rules. So take 30 seconds and think through within each of these which positions will be favored. And then maybe we'll do this just by way of a vote. And we'll see what people are thinking, which site gets the majority, the plurality, and if there are any where there's multiple factors that we need to weigh against each other, then we'll discuss that. Okay, so take 30 seconds here to think about it. Okay, let's go through it now. We'll ask for folks to raise their hands. We'll just go for each of these in order. Raise your hand if you think that's the most likely outcome. And then for each, we'll debrief and discuss if there's any confusion. So example A, 1, who thinks 1? Okay, that's getting quite a bit of votes. 2? 1 vote. 3? No takers for 3? 4. Okay, those who favored 1, why did you favor 1? Because you applied the rules that I just read out loud. Okay, for 2, what were you thinking that you were attracted to option 2? It probably will come down to this question of if you consider this metal to be highly electrophilic or not. Is that the crux of the question, but we would say here, this is molybdenum in the, what does it end up being? +2 oxidation state. Molybdenum is a middle or relatively early transitional. So we wouldn't say this is super highly electrophilic. So we would just call this that the normal wait. So sorry, let me. Oh, so we would call this, I guess, reasonably electrophilic. So we would call this addition to the terminal position. It's also cationic. Let me note that the overall complex is cationic. Okay, so now part B. Who votes for 1? 2? 3? Okay, that one was quite definitive. 2, 1 out there. And then last one, C. Who votes for 1? Who votes for 2? Who votes for 3? Okay. So anyway, I think as you work more examples, you can get a sense for this, how to apply these selection rules. I will say that, in your day-to-day life as a practicing synthetic chemist, you probably won't encounter complexes like this that have multiple potential sites of unsaturation and addition that often, or at least that's been my experience as a chemist. But it's good to know when you do encounter them how to think about it. Okay, let's then turn attention to the main focus of today's lectures, which are these metal-mediated alkene additions, or more generally pi bond additions. And so here we will consider 2 general mechanisms. We just saw in the previous examples cases that are strictly outer sphere. So what do we mean by outer sphere? We mean that the nucleophile is attacking from a trajectory that is outside of the coordination sphere. It's not engaging in any pre-association of the ligand to the metal center. We call that outer sphere. Other terminology that you'll hear in the literature would include nucleometallation, emphasizing the nucleophilic character of that incoming nucleophile. And then in the context of palladium-mediated additions, you also hear this described as a Wacker type addition. This honestly can be a little bit confusing because, as we'll see, Wacker type additions or Wacker process is a mechanistically complex series of transformations that can go through multiple mechanisms. So if you call something Wacker type, but Wacker type intrinsically means something that has a lot of possible mechanisms, that's confusing. But I just point this out, not because I love this terminology, but because you'll see it in the literature. So if someone's talking about a Wacker type addition, they're typically referring to an outer sphere type process in terms of the underlying mechanism. And then the opposite of that is inner sphere, where the key difference is that now you have pre-association of the ligand to the metal. And we already learned the basics of this elementary step because in the migratory insertion. So this then just looks like migratory insertion. And in the context of mediated additions, people will refer to this as a Heck type addition, and we'll talk about why that is. In any case, upon addition of this nucleophile, let's say in the inner sphere process, now just like in what we saw in migratory insertion, you open a coordination site that you would need to block to suppress the reverse reaction. In the outer sphere process, one of the things that you'll note here is that because you don't need a site of pre-association, you don't have a free coordination site, a vacant coordination site that you need to block in this case. So again, that's why in the the Green, Davies, Mingos rules, those are already coordinatively saturated, and they're not upon addition. They can still maintain coordinative saturation. So the when we're digging into this general concept of metal-mediated alkene additions, we need to take into consideration that metal alkene complexes, metal olefin complexes can possess this spectrum of reactivity depending on the properties of the metal, the coordinating ligands, the oxidation state of the metal, and so forth. So this continuum ultimately reflects how electron donating the metal is, and thus how extensively it's engaging in high back bonding. In one extreme case, metal olefin complexes, so the two limiting scenarios along this continuum, in one case, metal olefin complexes can be viewed as metallocyclopropanes. When the metal is an early metal and electron rich, then these types of species can actually possess delta negative character at the carbon atoms. And I think for organic chemists, one of the most familiar manifestations of this type of reactivity would be in the Kalinkovich reaction, where you have a titanocyclopropane that's generated via low valent titanium interacting with an olefin, and that's so nucleophilic at carbon. Think of these as like double Grignards, 1,2 bis Grignards. They can engage even unactivated carbonyl compounds, esters, ketones, etc. Where we're going to center most of today's class is in this opposite scenario, where the metal, by virtue of being a late transition metal and a relatively high oxidation state, will be electrophilic at carbon, so delta plus. And one way in which I like to think about this is that these types of metals will engage in pi Lewis acid activation. So they're like Lewis acids that we're familiar with, but we call them pi Lewis acids because they're selective for coordination of pi bonds. And they effectively pull that pi bond. They remove electron density from the pi bond, changing its character from being nucleophilic in the ground state to now being electrophilic and capable of being attacked by incoming nucleophiles. So this is always something to think about. Not every metal, when it coordinates to an alkene, is going to make that alkene electrophilic and prone to attack a nucleophile. It can have, in fact, the exact opposite effect. You really need to unpack, is this an early metal, a late metal? Is it overall charge cationic? Is it anionic? What's the oxidation state of the metal? And the best way to in your own mind, develop this predictive framework is to do as many examples and read as much as you can. Okay, now let's talk about the Wacker oxidation. In the previous two lectures, we talked about some of the very early industrially important applications of homogeneous catalysis, hydrogenation, hydroformylation, carbonyl insertion processes like Monsanto acetic acid process. Wacker oxidation is right up there in terms of historical importance. One of the earliest examples of homogeneous catalysis applied in industry. So I'll give you a little bit of a historical flavor because this topic is near and dear to my heart for the genesis of this reactivity paradigm and then ultimately its translation into synthetic methods that we're familiar with today. I direct you to this historical review in case you're interested in reading more about early history. This is a really nice historical perspective that came out in Angevante now a little over a decade ago, but is still I think one of the authoritative sources for history of Wacker oxidation chemistry. Okay, so in the reaction that we now think of as Wacker oxidation had a very humble beginnings. In the late 1800s, remember at this time, analytical techniques in organic chemistry were very rudimentary, and that they would include things like taste test, flame test, etc. So to get any idea of what functional groups were present in your mystery organic molecule or extract, you needed indirect methods. And one of the indirect methods that people would turn to is this process, which is called the Phillips alkene test, where you would take your mystery compound, and if it contained an olefin, what would happen? You would get oxidation of this olefin, now with one equivalent or probably even excess metal here. You would get oxidation of the olefin. And concomitantly, you would get generation of palladium black. So the way this test worked is you have your mystery extract, you add palladium chloride in water. If it turns black, it had an olefin in it. What's happening to the organic part? That people were not as interested in. They were just using it as a diagnostic tool to see what functional groups were present. It then took the better part of half a century for this to catch on as a tool in preparative chemistry. And the key innovation is, of course, if you're going to develop a synthetic method that is stoichiometrically consuming palladium, that's not a good starting point. So you're going to have to turn this over catalytically. So that's the whole name of the game here. That's the key innovation that allows this to work. You've got to turn over this cycle. And the way that we're going to do it is to couple it to a copper redox cycle that we're then further going to couple with reoxidation to O2. It looks very similar actually to how aerobic oxidation processes in nature look, where you have multiple catalytic processes coupled together. And so overall, this is going to bring about conversion of, do I have these? Conversion of ethylene to acetaldehyde. So when we talk about the Wacker process, that's specifically referring to this industrial process of conversion of ethylene to acetaldehyde. We'll talk about Wacker type reactivity, where we're saying the mechanistic features of this commercial process are applied in a synthetic context. But Wacker process, the only substrate that is used is ethylene. In terms of some of the history here, this reaction was discovered and developed by Walter Hafner, a chemist working at Wacker Chemie in the Ruhrgebiet, the Ruhr region of Germany, which is a coal mining region of Germany, kind of equivalent to the Pittsburgh of the United States. And it's an interesting example of a name reaction that is a name reaction, but bears the name of the company, not the name of the chemist who did it. I guess similar to like a Upjohn oxidation. So I don't know what it is about alkene oxidations, but the company seems to always get the credit in these cases. We mentioned that it's one of the first examples of homogeneous catalysis on scale. So why was this the topic of research, and why was this something that people were interested in developing in a commercial process? Well, if we go back to that period in time, this is post-World War II Germany. And Germany was in the process of rebuilding from this war, and they were developing all these new processes. We've seen so much rich organometallic chemistry come out of this period between the 50s and 70s of post-World War Germany, and this is another example of that. And it has to do with the fact that at that time, many of the most industrially important compounds, such as vinyl acetate or vinyl chloride, were ultimately produced from acetylene, which is ethylene, but at a higher oxidation state, has more potential energy. Where does that acetylene come from? It comes from calcium carbide. And that overall is a pretty expensive process. You would love to be able to make these same feedstocks, vinyl acetate and their equivalents, from ethylene. And that became an especially attractive value proposition because a new refinery called the Esso refinery in this Ruhr region of Germany came online. So we had access to cheap and abundant ethylene, and then the question is, what are we going to do with it? As the story goes, the attempted reaction by Walter Hafner was this interesting looking process. I'll leave it to you to think about how this might work mechanistically, what their hypothesis was, or maybe they didn't have. I'm sure they had some hypothesis, but this would be quite an interesting transformation in its own right. They're trying to make ethylene oxide from ethylene and O2 using heterogeneous palladium on carbon. And as the story goes, they set up this reaction in their reactor, and they open it the next day, and they immediately know that they did not make ethylene oxide. Why? Because if you've interacted with aldehydes before, you know they have a very pungent smell. So they open the reactor, they smell that they had not made ethylene oxide. It was immediately evident what they had made. No NMR required here. They had made acetaldehyde. And then there are a number of innovations, both in terms of the design of the catalytic cycle, the aerobic redox couple, but also in terms of the engineering to enable this type of reaction to be commercialized. Sometimes for these feedstock interconversion processes where the profit margin is very small, engineering considerations are just as important as scientific considerations. One of the key findings here, I won't go into these details in the interest of time, but was the development of titanium-lined reaction vessels, because some of the aspects of this overall process are not compatible with the vessels that were used at the time. So I'll fast forward now through history, and even despite the fact that this has been used now on planet Earth for the better part of 75 plus years, there are still some mechanistic mysteries. Not for a lack of trying, but as you'll see, I think it's an example of like, similar to Heisenberg's uncertainty principle as it applies to organometallic reaction mechanism. To understand the system, you need to perturb it in some way that takes it away from its native state. And once you've done that, you have this lingering question of, did I study the real system or not? That will hopefully become clear what I mean by that in a moment. Okay, so let's take a look now at the experimental rate law. So this part is not ambiguous. This is just coming out of the empirical data. It's known that under the industrially relevant conditions, the rate law takes this general form here. Positive order dependence on palladium tetrachloride, which is generated in situ under the reaction conditions from palladium dichloride. This is the soluble, aqueous soluble form of palladium dichloride. Positive order in ethylene, negative second order in chloride, negative order in proton. And then you can perturb the reaction conditions. So one way that people have perturbed the conditions are so the industrially relevant conditions are low chloride concentration and low copper concentration. And then you can perturb this, run at high chloride concentration, high copper concentration. And you can get a different experimental rate law. And the main difference here is that now you're only negative one order, negative first order in chloride, and you no longer have a proton term in the denominator of the rate law. So what does this mean? Well, I think one way to think about rate laws is that, and you've seen this before in class, but we'll unpack this in a little bit of detail here, just because it's a nice opportunity to refresh our memories. What is a rate law telling you? It's telling you in the context of catalysis. Typically in most monometallic catalytic reactions, you'll have positive order in the metal catalyst that you're using. So that's not a surprise. And then the other terms essentially tell you what you need to add or remove from the resting state to the transition state to enable the reaction. So we can just apply that framework. We need to remove 2 equivalents of chloride because that's in the denominator. We need to add an equivalent of ethylene, and we need to somehow remove an equivalent of H+. What does that mean? Well, that probably is going to come in the form of water. And we're going to lose that H+ to generate a hydroxide liquid. Why don't we have a water term in this
this rate law, you might be asking? Because water is one of the co-solvents. We have always a large excess. Basically pseudo, it's not pseudo first order. It's not, yeah, kind of like pseudo first order in a sense, but it's not first order. I don't know what the term is. It's saturation kinetics in water. Think of it that way. Okay, but this is still not totally right. So now we have, it should be overall -1 charge. Is that right? It's the transition state. And so the first thing, I think, based on everything you've seen so far, the thing that you would probably most reasonably draw is a transition state that looks like this, where you're forming the new oxygen-carbon bond and making this alkyl-palladium linkage. In this review article I've highlighted here, actually, they find that what they computationally predict, so based on kinetics, we could reasonably conclude this is the transition state. And the key point is that, bless you, is that now it looks like a syn oxypalladation, inner sphere, because we have evidence that the hydroxy is on the metal from the rate law. In this computational paper, what they think actually the transition state for the turnover limiting step is bond rotation about this bond. You can imagine that's high energy because you need to break up your chelating structure that is stabilizing. That detail is not that critical, but this is a nice article because it really outlines in clear terms these different mechanistic possibilities. And then in the other scenario, what do we have to do from this resting state? We need to lose a chloride, and we just need to add 1 ethylene. And now it should overall be what, -1? And then this would be consistent with water or hydroxide serving as the outer sphere nucleophile in this case. Does that make sense? How to go from these empirical rate laws to some insight about what the transition state would look like. The key point, the key takeaway from all this, if you don't like this rate law analysis, is just low chloride concentration, inner sphere, high chloride concentration, outer sphere. Intuitively, how do you remember that? If there's a lot of chloride present, it's competing for all the coordination sites on the metal. So the best the metal can do is like get one of the chlorides off, get the ethylene on, and then it's going to, the only way for the hydroxide, the only trajectory for it to come in is through the outer sphere. When you have low chloride, not much chloride around, then the metal has plenty of opportunity to swap on whatever ligands it wants. Maybe I'm the only person who finds that intuitive. I don't know. Sometimes I think, oh, this is a useful mnemonic device, but it's not useful to anybody except for me. And there are mechanistic details of this process that are still debated, but this is the key dichotomy, syn or anti. There are known byproducts from this reaction that give us a hint about reaction mechanism. So at high copper chloride concentration, one of the byproducts that is formed is, does anyone want to take a stab? This. Here, the copper chloride is acting in essence as a Cl plus equivalent. And so a common byproduct of the Wacker process is the corresponding chlorohydrin, where you intercept the oxypallidated alkyl palladium intermediate with this electrophilic form of chloride. We'll come back to that in a moment. Okay, so let's take a look now at a few selected mechanistic experiments that are of historical importance. We'll consider two, the first from, or two that are both from legends of organopalladium chemistry. The first from John Stille and the second from Jan Beckvall. So let's consider the Stille experiment first. So what Stille does is we take this doubly deuterated ethylene we're assuming the first step is going to be this oxypalladation to get to the alkyl palladium. And then we're going to treat this in situ with CO. What do we think might happen in this, in the presence of CO Philip? We have an alkyl metal plus CO.
Well, it could just coordinate to the metal and do
Okay.
formulation.
I love it. Coordinate to the metal. And then what?
Migratory insertion into the CO.
Beautiful. Now we have an acyl palladium, 2. And what could happen next?
Maybe beta hydride elimination.
What do we know, if anything, about acyl palladium species that contain a pendant nucleophile? Or what might we expect could happen?
Oh, cyclization.
Aha. And you could think about this mechanistically as being coordination to the metal center followed by reductive elimination. Here, I'm just going to draw it as a hydrolysis of sorts for simplicity. And then what would the product of this be, Philip? Corresponding lactone. And the deuteriums then are, I think I heard sin. Cis, yeah. Cis. So the important thing here in these deuterium labeling experiments, often a theme you'll see is that you need to cyclize. Why do you need to cyclize? So then you can analyze by NMR whether the deuterium's up or down. If you have an open chain substrate, that type of analysis to figure out where deuterium is typically not fruitful, unless in some special cases where you're conformationally constrained. So often in these labeling experiments, if you want to get to something cyclic, then you can use NMR as your diagnostic tool. Okay, and then let's consider this Beckfall example here. Now we're the high copper, high lithium chloride conditions. What do we think might happen in this case there? Dylan? I'll provide a hint here by directing your attention to this example.
An example that is, but
Up here.
have chlorine or Cl plus.
Love it. Okay, so we're going to displace this. Mechanistically, these details are not super important for the time being, but it's known that this type of conversion, alkyl palladium to alkyl chloride, happens with inversion of configuration. So I'll give you that piece of information. But I think you nailed it here, that we're going to need to form a carbon chlorine bond. I'm telling you that from previous work, this is going to happen with inversion of stereochemistry, like an SN2 type process. And then how would you get this to a cyclic structure?
We just close to get ethylene oxide, take
Beautiful.
out chlorine.
Just cyclize this down to the corresponding oxide. And what would we predict the stereochemistry to be now?
I would think it would remain anti.
It's anti in the open chain, and then we need to wrap it around.
Right. So we'll go to six.
Shut it. Beautiful. So this is a flavor of the types of experiments that have been done before, but you see already the complications. In the top example from Stille, they need to add CO. CO is not present in the commercial Wacker process, so you're perturbing it away from its native habitat. The bottom case, you need to use these high copper, high lithium chloride conditions that also are not native to the industrial process to get favor formation of chlorohydrin to get a product readout to inform on mechanism. So that's the open question. Are these industrially relevant. And that's why people continue to work on this to this very day. Okay, let's consider now, we've talked extensively about that key oxypalidation step. Let's talk about now some downstream elementary steps. So for that, we'll turn to problem of the day number 2. Consider the results of these 2 labeling experiments. In the first, we're going to take unlabeled ethylene and D2O, and we see no deuterium incorporation in the product. Second, we use fully deuterated ethylene and unlabeled H2O, and now we see deuterium incorporation into the product. So what would this tell us about the elementary steps downstream of oxypalidation? So take a minute to think about that, and then feel free to compare notes with your neighbor. I will sketch out some notes to get us started here. Okay, Jenny, help us out here. We've done our oxypalidation. What is our next step going to be? We've got a metal and a hydride / deuteride in a after bond rotation in a cis relationship to one another. So that will be a signaling element for what? Beautiful. Beta hydride. Now what? Okay. So now you might be tempted to just dissociate this enol and hydrolyze. That can also, if you push arrows, that can get you to the product. But what do we know? You know that the deuterium on palladium needs to get into the product, right? Exactly. So it will undergo hydride insertion from the opposite direction that it came in. And get us home here, Jenny. What's next? Beautiful. another beta hydride elimination, this time with this the OH, as you said, and boom, out pops your product. Now we have palladium hydride, and we have fully deuterated product. And because now there's no olefin left in this acetaldehyde, the coordination between the carbonyl and the hydride is weaker. So this is ultimately just going to find some base and regenerate palladium 0. It's not X, H. Rather than reinserting like we saw before. How do we know that it's not this enol type mechanism? Well, in that case, if we did this experiment with the labeled water, we might expect to see incorporation of deuterium from the D+ that's present in solution into the quote enol that would be freely diffusing into solution, which we don't see. So both of these experiments mutually consistent with this pathway. The key finding being that after the initial beta hydride elimination, beta deuteride elimination, it reinserts, and that to eject the substrate, you need to beta hydride eliminate off of the OH. That's the key point. And we'll see this come up again in some other examples that we will cover. Questions about that? Yeah.
Is there the experimental proof that the second step is also a beta hydride elimination?
As opposed to, what else would you like to draw?
Probably envision a base that's deprotonating the oxygen, push the electron to get the palladium away.
Yeah, this is an interesting and subtle point. So what we have covered mostly in class, and we'll cover mostly in class, are sort of canonical beta hydride eliminations, but there are more exotic beta hydride elimination mechanisms that sometimes you can't necessarily disambiguate from experimental data alone, but computationally will look reasonable. I think it's not so controversial to do beta hydride eliminations to generate carbonyl compounds with palladium group metals. I think that's fairly commonly accepted. So my understanding is that that's the prevailing mechanism here. But what you're proposing in terms of arrow pushing is reasonable. We've definitely had papers that, and what did I just do? Involve beta hydride elimination, where reviewers have asked us to compute non-classical mechanisms like what you're proposing. Okay, so we talked about the Wacker process as being this commercial process for generating acetaldehyde, but most of us are not working on PhD projects that are commercial, that are total syntheses of acetaldehyde. So where does this connect to our lives? Jiro Tsuji has made a number of really pivotal contributions to organopalladium chemistry. And one is the development of this laboratory scale version of reaction that accepts substrates that are not ethylene. And this is called the Tsuji-Wacker reaction in his honor. And the key addition here is using DMF as a solvent. Again, under conditions that are similar to the Wacker process. This reaction proceeds with reliable Markovnikov selectivity. It's so reliably Markovnikov selective that in the literature you'll read that you can view these methyl ketones as signaling elements or as synthons for using a Wacker disconnection to get you back to the corresponding alkene. And it proceeds through the intermediacy of this terminal alkyl palladium species. And a mnemonic here that I think is useful, although it's a little bit of a simplification, because certainly there is a major steric component to this as well, is if you think about a pi-Lewis acid activation mechanism, and you're asking in this terminal alkene, which of the two positions is going to build up more partial positive charge or more capable of stabilizing partial positive charge, you would say the internal position. And so again, as a mnemonic, I think this is helpful. Upon pilose activation, you build up partial positive charge to the internal position, and that's where the incoming nucleophile engages the alkene. So this is great for making methyl ketones. What if you want to invert this and instead get the corresponding linear aldehyde product? We've seen already in the hydroformylation lecture how valuable aliphatic aldehydes can be. How would you do this? Well, this is still somewhat of an unsolved problem. The state of the art was published in 2013, right before I joined the Grubbs group. Is published by the lead author of this study is Zach Wickens, who we just saw as a seminar speaker not too long ago. And he developed, Zach and the team developed this aldehyde selective Wacker oxidation. This builds on important prior art that I should highlight by the likes of Ben Feringa and others. Some of the key changes here compared to the classical Wacker are that we're using this interesting nitrite, silver nitrite co-catalyst running the reaction in T-butanol and nitromethane as co-solvent. These are somewhat unusual. And how does this work? Well, the upshot here, I should doubly underline this, is that the mechanistic details are still very murky, but at least what's proposed in the paper in a somewhat hand wavy way. I think I can say this because I was there when this was ongoing. Is remember that radicals like to engage with alkenes with anti-Markovnikov selectivity. So the idea is that there's some pre-association with palladium nitrite, perhaps, that coordinates to the alkene, and then the radical character of the bound nitrite can facilitate attack. And this is consistent with an experiment where they use labeled nitrite and see that the primary oxygen atom source of the product is the nitrite rather than the other things that you could imagine, O2, T-butanol, etc. As I said, this is not a completely solved problem. You see the aldehyde selectivity here is only 90%. I say only, but that's the state of the art. You could imagine if you ever wanted to do this on commercial scale to make feedstock chemicals, you'd need to be certainly greater than 99 to 1, or you'd have to have good infrastructure, engineering infrastructure to separate your product. So if you have good ideas for this problem, there's still an opportunity there. Internal alkenes also are historically challenging. This is another example I'll highlight from the Grubbs group. First author here is another chemist we're familiar with, Bill Morandi. And the trick that we use in this case is, maybe I'll take a step back. Why are internal alkenes typically challenging? It's because now they're more sterically encumbered. Everything becomes harder because the substrate is more sterically encumbered. How do we overcome that? We juice up the catalyst's reactivity by making it doubly cationic. So we come in with palladium-2, and then with this combination in DMA with HBF4 as an additive, we'll generate the biscationic palladium tetraacetonitrile complex. That's super pilose acidic, so that can activate even internal alkenes. And this is a modification of an original procedure from Canada. So internal alkenes you can use if you're in terms of synthetic planning, but you need to use some additional tricks. So that's why I include this reference here. Okay, and let's consider one more substrate class, and this will bring us to problem of the day number 3, styrenes. Styrenes in the alkene functionalization literature, sometimes we think of as being quite easy substrates, but in Wacker oxidation, historically, they're somewhat challenging. Why is that? Because they can engage in alkene polymerization as well as various oxidative fragmentation processes. A solution to this was developed by the lab of Matt Sigman, that's where this example comes from. And they make several modifications to the classical Wacker. They use this hyperligated palladium to pre-catalyst. Let's draw that up as you're thinking about this. Hyper, the I means the unsaturated backbone.
radium 2. Hyper is the 2,6 diisopropyl catalyst. And then it's the chloride bridged dimer. So here, we're not using O2 as a terminal oxidant. We're using another quite commercial terminal oxidant, one of the favorites, recent favorites of the ULab, TBHP, terbutyl hydrogen peroxide. Okay, so let's consider problem of the day number 3, which asks, two questions. One, design an experiment to determine the O atom source in the product. One or more experiments. That one I think can be somewhat quick. And then based on what you answer for A, after that initial oxypalidation step, you could envision many things happening, but there are really 2 limiting mechanistic scenarios. So consider what those might be, and then design an experiment to distinguish between them. And the hint here is that one of those mechanistic scenarios is somewhat different than what we have covered up until this point in the class. And then I guess from what I just said, you can infer that the other is similar to what we've covered in class. But maybe let's just very quickly together do A so that we can spend a little more time with knowing what the oxygen atom source is in thinking about B. So Annabelle, what is an experiment that you could design here? What are the possible O atom sources? The methanol. Okay. TBHP. And then what do I have written beneath TBHP here? I heard Annabelle say it, water. And then you could even, I mean, there are some more exotic options too, silver, triflate even, but I'll tell you it's not triflate. Okay, so how would you design a experiment to pin this down? What do you think, Annabelle?
I guess we cannot just label it because we just use labeled water and the methanol and the TBHP separately too.
Okay, beautiful. And what if you had to pick one of them to do first? What would you do first? I think practically you'd probably do the methanol or the water first, because those are going to be much easier to come by than labeled TBHP, selectively labeled at one of the 2 positions, right? So as it turns out, the experiment that works here diagnostically is to just label the water, and they find that that gets incorporated. There are some caveats here. What might you be concerned about? Well, if you were doing this experiment, you show this to your PI, what would they say? When you make a carbonyl compound under these conditions, you can have labels wash in and wash out. So how might you circumvent that or account for that? One way would be to just stop the reaction at the lowest possible conversion that you can. And that is indeed what I think they stop it at less than 5% conversion. They're already seeing some of the label wash out at that point, but they're able to get enough signal to assign water as the primary oxygen source. We've done these types of experiments before in the group, and indeed, anytime you incorporate a label into a carbonyl, you need to be really careful and do your control experiments to make sure that you're not fooling yourself. Okay, now
next part of the question, what's going to happen? Oh, sorry. What? Gosh. Camille, you should have like raised your hands. They use O18 labeled water, and they showed that it's not present in the product. You can do a similar experiment with methanol, and ultimately they pin down. I'm trying to confuse you absolutely as much as possible today. So they find that the TBHP is the source of the water. And I'll give you a hint that it is this of the oxygen product. Okay, so now that we know that the initial oxypalidation is taking place by TBHP, let's draw what that product will look like. Okay, so what are the potential mechanistic scenarios here? Christine, what do we think based on what we just covered?
Can you do beta hydride elimination?
Beautiful, okay. So beta hydride eliminate, that's going to get us to, there's different ways you could draw this, but just bear with me here. That would get you to something that looks like this. And then you can imagine the palladium hydride that's generated reducing the oxygen-oxygen bond of the peroxide. What would be another possibility? No bad ideas here. Anything that's on your mind? Open this to anybody. Shenghua, what do you think?
Maybe cleavage of O bond first.
Okay. So that you'd oxidize, I guess, to palladium 4 in that case, but then you'd still beta hydride eliminate. Is that right?
Yeah.
Okay. So I would call that similar mechanistic scenario, but maybe in opposite order of steps. That one's probably less likely because palladium beta hydride elimination from palladium 4 alkyls is slow compared to palladium 2 alkyl. Any other thoughts?
Do a beta oxygen elimination.
Okay, but that would just be the reverse of what you did to. Another possibility that will look a little bit familiar, sort of a quasi-pinnacle type rearrangement, would be a shift of this general type. So it's an H atom 1,2 shift mechanism. And that, if you push arrows, is going to get you to what will that get you to? Here, then you'll have some palladium 2 butoxide species. So how might you disambiguate between these two possibilities? Juntao, what do you think?
to see whether it's the palladium hydride can be detected in the reaction.
Okay, but that's not a bad idea, but I would say that can be challenging because you then are depending on the palladium hydride being an observable resting state.
Or maybe the alpha protein.
Aha, aha. I like what you're thinking here. And what would you expect to happen? You deuterate this position.
It's a palladium hydride mechanism. There is no deuterium in the product.
Bingo.
The second mechanism, the deuterium will be on the
Beautiful. And that is indeed exactly the experiment that Sigmund Lab does. They observe this product and they conclude that it is a 1-2 shift mechanism, which is, I think this is related to the question Wenji is asking. There's a lot of different ways you can formulate what would be formally a beta hydride elimination. This is one. And you might ask yourself, how general is this? And I would say not that general. You don't have to think about it in every situation, but it is known that when you use these peroxide at oxidants / O atom sources in palladium chemistry, that this is a possible pathway. So within this particular subfield, this is something to think about. But in general, if you didn't know better, then proposing the top line or something to that effect would be fine. Any questions on this before I move on? Okay, let's talk about other types of nucleophiles beyond oxygen now. So one of the features of this general reactivity paradigm that has enabled it to be an enduring theme in organic chemistry is that it's not just limited to water as a nucleophile. If it was just limited to water as a nucleophile, we'd probably have solved everything there is to solve at this point. But you can use other types of oxygen-based nucleophiles, carboxylic acids, phenols, etc. And you can use other categories of nucleophiles, carbon-based nucleophiles, and nitrogen-based nucleophiles. And we'll see how this research in the context of carbon-based nucleophiles will set the stage for both the growth of the fields of allylic substitution and cross-coupling. Okay, let's first consider I think this is the first, or certainly one of the first 2 or 3 examples of CC bond forming reactions mediated by palladium, well-characterized processes mediated by palladium, by the lab of Jiro Suji, familiar name. 1968, he takes this palladium chloride Ka dimer and reacts with malonate. What happens here? Simple pi-Lewis acid activation mechanism. Malonate attacks one of the 2 alkenyl carbon atoms. We have a transannular chelation stabilization. So the alkyl palladium, which normally might be prone to beta hydride elimination, is locked in its track, so to speak, and you form a new CC bond here. Why was Suji interested in this? Look at the time period. This is right when Wacker process is coming online. So people are very much asking this question: what other nucleophiles might you be able to bring in with this reactivity paradigm? It then took the better part of 4 decades, 5 decades even, to render this process catalytic, where you integrate a CC bond formation from a CH pronucleophile like a malonate and turn that over catalytically. And this was developed by one of my heroes in organometallic catalysis, Ross Wiedenhofer at Duke University. One of the key references you can read for yourself down here, and we'll send this out for the read. I just show some of the results of catalytic of the labeling experiments that were done that show you some of the complexities of this process. So the overall transformation is what? We're going to take this tethered alkene that contains a CH pronucleophile. I've set this up. So we form an enolate or an enol. We're going to have pi-Lewis acid activation to form a new CC bond here and a new carbon palladium bond here. And we then have a series of chain walking events to migrate the palladium from this alkyl position to the alpha position, the other alpha position. How do we know that? Because in this mechanistic experiment, we see deuterium incorporated into this alpha position. Palladium enolates, as we have talked about a little bit, benefit from some of the same stabilization of benzyl palladiums, al palladiums. They can exist in the C-bound form as shown here. They can tautomerize to exist in the O-bound form. So this is a stable position. So palladium has a driving force here to want to chain walk to get to a stable position so that it can engage the proton or deuteron, which is a slow step. And then similarly, we can take labeled alkene here, and this will allow us to deduce. So the first step allows us to deduce, the first experiment allows us to deduce what happens after carbopalladation. And this experiment will allow us to deduce what happens during carbopalladation. So we do this experiment, and we would expect if this were a syn carbopalladation versus anti-carbopalladation, the relative stereochemistry of the two deuteriums would be opposite. We see in the final product that they're on the same face of the alkene, consistent with an anti-carbopalladation process. I went through that quickly, but the key point here is that overall, this process, it has some of the similar steps of the Wacker. You could consider this like a carbo-Wacker, but with the twist that instead of a beta hydride elimination, now you're protonating the carbon metal bond off. The overall catalytic cycle thus is redox neutral. And actually, I think still to this day, the direct carbo analogy to a Wacker, a carbo-Wacker, it remains undeveloped, or there's the reports out there are not very convincing. And I'll leave it to you to think about why that is. What about nitrogen nucleophiles? Well, here too, in the 70s, this was already the topic of interest. So early work from the lab of Bjorn Ackermark. He's like the godfather of organopalladium chemistry in Sweden. So Jan Beckvall trained with him, Lou Hegedus trained with him during his postdoc. Ackermark developed a protocol for aminopalladation stoichiometrically, where you can engage these NN dialkyl amines to give isolable alkyl palladium intermediates of the general type shown here. And then these intermediates you can take further, for example, react them with H2 in a formal hydroamination, react them with oxidants, et cetera. But it took a few decades here to start efficiently turning this type of reaction over catalytically. Why? Because the coupling partners that were initially used are these dialkylamines, which can be relatively strongly coordinating to palladium, certainly competitively coordinating with the alkene substrates. So your coupling partner is a catalyst poison, and that's never a good recipe for efficient catalysis. A key realization by several groups, including one that I'll highlight from Shannon Stahl, is that if you operate within a certain pKa range, a certain coordination strength of your nitrogen nucleophile, then you can turn on catalysis. So that pKa range is something like 18 on the low end and maybe 25 on the high end. So think here things like imides, amides, carbamates, anilines, sulfonamides, etc. So this example with a cyclic imide from Stahl, this works well, terminal alkenes, cyclic alkenes. The conditions, I think, are pretty reminiscent of classical Suji Wacker. So really the realization here is all about the nucleophile. So we've shown cases where you can do several different things, several different steps after this initial nuclear pallidation. Beta hydride elimination is the classical one. We showed in that mechanistic experiment by Stille that you can react also with CO in carbonylation, just slip in a CO into the carbon palladium bond. We've seen in that Wiedenhofer example that you can protonate off. Additionally, you can react with oxidants. So in this case, phenyl iodobenzene diacetate reacts as an acetate electrophile, and that will engage a palladium 2,4 catalytic cycle to form carbon-oxygen bond. So I've represented this here in the context of intramolecular examples, but you can imagine doing those intermolecular examples as well. There are some additional challenges. There's a review here from Shan Stahl from more than a decade ago, but still is quite informative. And a key point I want to make here is that in terms of the underlying redox, it's fairly diverse. So in the classical beta hydroelimination pathway, you have palladium 2,0 redox chemistry. In these types of difunctionalizations, you have palladium 4, 2,4 redox chemistry, carbonylations, palladium 2,0 chemistry. And then in that protonation, it's all palladium 2 or palladium 2,2. So just giving you a flavor for how you can take one elementary step or a collection of related elementary steps and parlay them along a number of different fates in terms of the catalytic cycle. There's a related body of work from one of my other heroes in organometallics, and actually one of my undergraduate instructors, John Wolfe. And he's developed a way to do what on the surface look like similar reactions, but mechanistically are different. Here, he generates a palladium 2 aryl species via oxidative addition of an aryl halide to a palladium 0 catalyst. And these palladium 2 aryls are still sufficiently Pi-Lewis acidic that they can coordinate to an alkene and trigger nucleopalidation to give these difunctionalized products. This borrows some steps from cross-coupling that we'll see, we'll learn more about. These elementary steps of oxidative addition, transmetallation, reductive elimination, the holy trinity of organometallic catalysis, so to speak. So it borrows concepts from that, but then engages nucleopalidation mechanism. Okay, let's consider a couple other examples. So here's an intramolecular catalytic hydroamination from the lab of Forrest Michael. This, I think, is a nice example of outer sphere aminopalidation. So we take this PNP pincer, highly electrophilic catalyst. It can coordinate to the alkene, trigger nucleophilic attack of nitrogen to get a stable alkyl palladium intermediate. This is coordinatively saturated, so it doesn't have the opportunity to undergo beta hydride elimination. There's no open coordination site for the syn beta hydrogen to find, so it's stuck there. But in the presence of triflic acid, which is generated in situ from the additive copper triflate, then this can be protonated off. And this is I think the only time I'll show an example from our own group's research, but I think it actually connects here. So then the question would be, how would you make this type of reaction intermolecular? So if you can close to form pyrrolidines and piperidines, et cetera, that's useful, but ideally you'd like to be able to do this intermolecularly as well. How would you do this? Well, the trick that we play is to essentially build the ligand into the substrate, at least in our initial manifestation of this idea. So we make the substrate polydentate coordinating. And if I get this wrong, then you really can, you can judge me harshly. So our substrate mimics that same coordination environment that you find in the Forrest Michael chemistry. Now a nucleophile, an attack. We've done this with nitrogen nucleophiles, carbon nucleophiles, oxygen nucleophiles. This ends up giving a metallocyclic intermediate, a 5,5 Caleta bicycle. Which then we can react with a proton to give the overall transformation of an intermolecular hydrofunctionalization. Regiocontrol, even with internal alkenes that do not intrinsically possess electronic bias. And you might ask, how does the regiocontrol work? And this is actually an interesting and still emerging story. Sorry, I realized I lost the video signal. Our current best hypothesis is that the initial steps here are reversible and that regioselectivity is determined in this trapping step, this protonation step. Okay, any questions? We have, okay, let's go to problem of the day number 4. And we'll maybe come back to some of the notes I have here because it connects to some of the allelic substitution chemistry. So problem of the day number 4. Let me share that. So let's take 2 minutes to think about this. Some familiar ingredients. So we have a CBZ protected nitrogen nucleophile here. Remember what I said is that carbamates are some of those proud, the few and proud nucleophiles that work well in Wacker type additions. And we have a allylic alcohol as the substrate. The ligand here is a pyrox ligand, pyridine oxazoline ligand. You see it has an electron withdrawing CF3 group, so you can imagine that's there to enhance the electrophilicity of the palladium catalyst that's generated in situ. We have BQ, which is benzoquinone, which is a terminal oxidant that's commonly used in Wacker type reactions. DTBMP, which is an organic base, and then the rest of the details are not that critical. So what might we expect is going to happen here? The ligand's chiral, so that's one signaling element. So these go hand in hand, but we'll think about the product, mechanism, and then if as an extra credit, you want to also think about experiments that you might do to support your favored mechanism or refute other possibilities, then that is of course welcome, and we can discuss those. Okay. What do we think here? Who haven't we called on yet today? Elin, what do you think? Okay. at the alpha position with respect to what?
Or the terminal position.
Okay, this, I think, if I understand you correctly, you're saying this position. That's, you can appreciate as a chiral center. One, two, 3. All right. And then how are you thinking about this mechanistically?
Video will connect on the open first. We have the hybridization.
Okay.
File attack.
Let me try to catch up with you here. So you said aminopalidation. And then, was that right? Beta hydride elimination. And then what next? Reinsertion?
So mental research.
Reinsertion, just like the, I think you said just like the Wacker. So we need to get to that. Need to get to this key intermediate. Your last beta hydride elimination will take you home. And then you will go on to reoxidize this palladium hydride. So this will be quenched with the base to make palladium 0 and the HX, and then it will get reoxidized to get back on cycle as palladium 2. Okay, very good. And did you think about the extra credit? How would you, let's say one of the things that you might be curious about, we all might be curious about based on the discussion today, is in this CN bond forming step, is that syn or anti?
I'd like to, in this case, would be, I guess it's syn.
You would guess it's syn, okay.
All the amino cyclize, like get the synchronization cyclized product.
Okay, so you want to deuterate the olefin here? Is that what you have in mind, Elin? I think that's doable. Let me see, would that be diagnostic? But then you're, so then you're going to see where the deuterium is with respect to what? Where the deuterium is with respect to the, like the methyl group. Is that right? Okay. That's, I think that's a reasonable thing to think about. If I remember right, I think what they do in practice, really for synthetic ease as much as anything, is to use this type of structure. You can make this from reduction of the corresponding aldehyde with deuteride, or the corresponding carboxylic acid oxidation state with deuteride. And then you will see that this D will ultimately get incorporated here. One of them will end up being here, and the other will end up being that, right, will end up being right, yeah, so one will end up being here, and the other will end up being at the aldehyde, and then you can cyclize it down and see the relative relationship between that deuterium label and the methyl and make your stereochemical assembly. Same idea, I think, just synthetically a little bit more tractable. And our chemist of the day, does anyone recognize? Was the first author of this work during her postdoc with Matt Sigmund. This is Anna, sorry. The institute, maybe you can get from the hat. You see Riverside, our neighbor to the north. In addition to this important study, which I'll write up the reference for in just a moment, Anna has a very nice review article. Let me put the review first. Because we're out of time, I'll put this review up, and then this review contains this original reference, so you can consult that. And Anna, as I said, did her postdoc with Matt Sigmund, did her undergrad or grad training with Malchiori at ICIQ. And in her independent career has been working in the area of nickel catalysis. So this is a nice trend. This Trends in Chemistry review is a nice summary of enantioselective approaches, both in the Wacker and the Heck reactivity paradigm. Okay, so we'll kick things off next time by now segueing into other types of pi systems, particularly those that can lead to pi-al species, and that will be a natural springboard for the discussion of pi-al substitution chemistry, and then off we will go to study other catalytic reaction systems for the remainder of the semester. So as a reminder, stick around if you want to receive your midterm back, and otherwise we'll see you next week.